Here's another short script for Math156, again based on a single example from the textbook. This is in section 3.7, and I'd encourage you to have your textbook open to page 64 while you are watching this video. What we're going to do is compare some actual data with a probability model for the data. The actual data consists of the fourth of a year in which the birthday falls for each of a rather large number of soccer players. So here are the data of observations, and what it says is of these soccer players, lots of them were born between August and October, lots between February and April, but surprisingly, a comparatively small number were born in May, June, and July. And the question is, are these data consistent with the hypothesis that birth date is equally likely to fall in each column of the year, each quarter of the year for athletes? Well, we can compute what the expected number of birthdays in each quarter would be if everything were uniform. We just make a vector of length obs, that's a length of 4, in which each entry is the number of observations divided by 4. So that's it. If everything were uniform, we'd have 132 birthdays in each quarter of the year. Now let's compute chi-square for this table of one row. The expected number is exactly what we just calculated, and the chi-squared statistic, as always, is the sum of the quantity that you get from summing over all 4 entries in the table, observed minus expected squared divided by expected. If I look at the result of this function, I get 10.9697, and that's exactly the number that's calculated in the middle of page 64 of the textbook. I'm just doing exactly the same calculation. If you run chi-squared test on the observed data, you get a p-value of 0.012, and what that says is the probability that you get this large a chi-squared value by chance is only 1.2%. Now we know how to test that by brute force computation. We'll make a probability vector with 4 entries. I'll call it months, and these are just the 4 ranges of months. And we can sample from this vector to get our 4 times 132 observations. So here is the vector birth.sim. If you look at the first 6 entries using head, it's just lots and lots of randomly chosen trios of 3 months. We can make a table from it. This is, of course, not exactly the same set of numbers in the textbook. And if you look at it, you say, those numbers look much closer to 132 on the average than the ones I saw in the textbook. So now the question to ask is, how often do you get a chi-squared value out of such a simulation that's as large as what we saw from the observations? We can certainly call the chi-squared 1 function on this table, and we get 0.95, which is a good bit smaller than what we got from the actual data. Now we just do this simulation over and over and over again, 9,999 times. We generate a sample of birth quarters of the year, store the chi-squared result in the ith entry in this great big numeric vector, plot the result. You've seen that before. It looks like a chi-square distribution. The red line shows the value of chi-square for the actual observations, and you can say, aha, The probability of getting a chi-squared value from randomly generated observations that is as large as what we got from the real-world data is pretty small. To be precise, if I calculate the fraction of the time that the result is greater than the actual observed chi-squared, we get the p-value, and this is very, very close to 0.012, because basically what the chi-squared test does is to try to simulate the result of a permutation test like this. Here is a histogram of the results. This time I set probability equal to true. That means that I can compare with a density function. What do I want to compare with? I want to compare with the density function for chi-squared with 3 degrees of freedom, because we've got 4 entries in the table. But once you have any 3 of them, you can calculate the 4th. So there are only 3 independent ones. And not surprisingly, we get a nice matchup with the chi-squared distribution function. And that's all I have to say on this very short example.